Okay.
How come all the other parties cannot see? Now in my screen, I can only see 5 of us, you know. You mean the rest of the people, we cannot see their face, huh? 6 of us now. Only 6
Because
person.
they close their video.
Oh, they can open now.
It's up to them actually.
Surprisingly low attendance, huh? I thought 1,000 people not enough space, you know.
Mr. Zack
Now
is
I'm
here.
on my desktop, doctor. Can I use my iPhone to enter one more time? Is that?
Sure, can. But you have to close the
No, can I use my iPhone to? But just now dua pun ada tau. Then it come out my name Alex Liu. But this one, it comes. Now come out. See?
Not clear, Mr. Alex. Okay, now it's already 2:15. Dr. Isan, should we start or we have to wait another 15 minutes?
Okay. You can start, Prof.
Okay, Tori.
Okay.
Prof. Fazil,
boleh start, Bu Elo.
Yeah, okay. Allow me to open this event. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. May Allah subhanahu wa ta'ala bless us with His mercy and give us health, protection, and happiness. Welcome to you all to CSM International Webinar on Construction Material in Greenation Era. Series 2, Construction Technology Moving Forward. Friday, 4 December 2020. Ladies and gentlemen, I would like to welcome our keynote speaker for this afternoon. We have keynote speaker, Professor Dr. Megat Azmi Megat Zohari from University Science, Malaysia. And then second, Dr. KMC Konte Singha from University of Sri Jayawardenepura, Sri Lanka. And then the next keynote speaker, Mr. Liu Chung Meng from Solid Housing Solution IBS System, Pahang, Malaysia. And for our moderators this afternoon, for our moderator this afternoon, Associate Professor Dr. Muhammad Fazil Arsad from CSM and UITM Shah Alam. And then also Dr. Iksan Setiawan from Narottama University, Indonesia. So, ladies and gentlemen, before we start this event, let we hear opening speech from Professor Fadil Arsad. Professor, you can give your speech for this opening in this event.
Okay. Hello, Assalamualaikum and Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. Thank you to our chairpersons, Elo Damayanti, to respected Dr. Ihsan from the Narottama University, our speaker Dr. Shaminda, Prof. Megat, and Mr. Alex. Thank you for agreed to become a speaker for this lovely morning. This lovely afternoon. On behalf of the organizer, Concrete Society Malaysia, University Technology Mara, University Tun Hussein On Malaysia, American Concrete Institute, and also Narottama University, we would like to say thank you very much and welcome to the webinar series. This is our second series that been successfully conducted for the last stations. And hopefully this session also will be very great to be shared with all the participants on today's webinar series. As we all know that concrete is the main materials that been used in the construction nowadays, and in the new era, people are keep on looking for the green technology and green concrete as well. So on that matters of concerns, we are from the Concrete Society Malaysia, very happy to have these sessions, and we have been very appreciate all the knowledge, informations, and the technologies that are going to be shared with all the participants in this lovely afternoon. In this lovely afternoon, we've been very great because we have three speakers that we have been invited, which is Prof. Dr. Magat. He is the professors. He's my professors actually. I've been doing my PhD with Prof. Magat. He's a great supervisors and great teachers as well. And then I got to know Dr. Chaminda in Sri Lanka on the last visit to Sri Lanka in 2019. And then my good friend, Mr. Alex, who I've been very supporting uh, for Concrete Society Malaysia. Um, and we are feel very happy because they are ready to share all their information, knowledge with all of us in this late afternoon. All right, so that will be my opening speech. Hopefully that all of us in this session can gain as much as knowledge that we can get from all the speakers. And to all the participants, thank you for joining us. You are welcome, and we are looking forward for next program as well. And then we hope that you can ask questions to the speakers regarding on the matters that have been discussed. All right, so without further ado, I think we should start our sessions with recite the doa. Hopefully that Allah SWT will give bless to all on our program. So we start with Al-Fatiha. Auzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Arrahmanirrahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Amin. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu ala sayidina Muhammadin asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. يا ربنا لك الحمد كما ينبغي لجلال وجهك وعظيم سلطانك اللهم اغفر لنا ذنوبنا ولوالدي وارحمهما كما ربونا صغارا ربنا آتنا من لدنك رحمة وهيئ لنا من أمرنا رشدا وصلى الله على سيدنا محمد وعلى آله وصحبه أجمعين سبحان ربك رب العزة عما يصفون والسلام على المرسلين والحمد لله رب العالمين. الحمد لله. So hopefully with the dua, Allah SWT will bless all of us through this program, and will let's the program become a good program for us, and let's the programs become a link for us to start or to have a collaborations between all the participants and the speaker as well. All right, so without further ado, I would like to call upon our first speaker, which is Professor Dr. Magat Azmi Magat Johari from University Science Malaysia. Prof, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all. So first of all, I would like to thank the main organizer, Concrete Society Malaysia, co-organizer, University Technology Mara, UTHM, ACI, as well as Narotama University. Okay, and special thanks to Associate Professor Dr. Muhammad Fadil, okay, Dr. Ihsan, okay, for inviting me to be one of the speakers. Okay, also thanks to fellow speakers, all right, and also Dr. Warid, okay, and also to all participants. Thank you for joining the event this afternoon. All right. So the name of the event, CSM International Webinar on Construction Material in Greenation era. Sorry. So I try to come up with some presentation that hopefully will fit the theme of the webinar, as well as construction technology moving forward theme, I believe. Okay, so I try to share the screen at the moment. Can you all see the slide?
Yes, Prof.
Yes, we can see.
Okay. So I give the name or title to my presentation as Towards Sustainable Concrete, Revisiting the Roles of Supplementary Cementitious Materials. Okay. So to most, maybe this is a revision. I'm not sure. So probably there are some who may find this presentation beneficial. Okay, hopefully, I do hope so. Okay. Anyway, I give it this title and trying to fit the theme of today's afternoon webinar. Okay. So my name is Megat Azmi Megat Johari from the School of Civil Engineering, University of Science, Malaysia. All right. So as introduction, okay, so we know about the waste generation throughout the whole of the world, okay, and we can relate this waste generation to sustainability. So it is unsustainable if we cannot dispose the waste properly, okay. And in terms of sustainable construction, okay, it's always been associated with some of these, using renewable and recyclable resources, right? Reducing energy consumption as well as waste, then creating a healthy, environmental friendly environment, as well as protecting the natural environment. So these are among the characteristics of sustainable construction, or what has been done as practices in sustainable construction. So I believe if we try to produce concrete that takes into consideration this characteristic or these practices, we are moving into sustainable concrete, also into sustainable construction. Okay, so that's the first part of the introduction. All right, so this is the current scenario. So in terms of global cement demand and consumption, cement as well as concrete. So from here, all right, from the data from 2013, 2018, we are seeing a steady increase in terms of demand for cement and concrete. Okay, and in terms of utilization, the use of Portland cement concrete is second to water, meaning that it is highly demanded throughout the world. Okay, and we are expecting that the demand for and the production of conventional Portland cement concrete are expected to rise significantly based on the current scenario as well as in the future. Okay, and this demand is expected to be much higher in the case of high strength and high performance concretes, which are being increasingly utilized in the current and future construction scenarios, right? So meaning that as we going towards high strength and high performance concrete, the main thing is that the binder content has to be high, meaning part of the binder should be Portland cement, and the cement component should be high in that manner. And that also will lead to greater demand for cement in this particular type of concrete. All right. And the negative point of view is that cement production has been linked with environmental problem. Okay. In particular, greenhouse gases emission, and it is also being extremely energy intensive processes. Okay. And for example, to generate or to produce 1,000 kilograms of cement, so it is estimated that about 900 kilograms of CO2 is emitted into the atmosphere. Okay, and cement industry contributes between 5 to 8% of global man-made CO2 emission, right? And the production of cement, which require extensive amount of non-renewable natural resources. So the extraction of these non-renewable natural resources could pose unnecessary threats to the future of the cement and concrete industries, all right? So this is the breakdown in terms of CO2 emission from cement production. So we can see that, so mostly it is contributed by cement clinker production, or the calcination, as well as carbon fuel burning for heat and other processes as well. For example, the raw material preparation and grinding, as well as transportation. So almost the major parts of the cement production processes is associated with emission of CO2 into the atmosphere. All right. So if we look at the projected demand, okay, for cement, so we are seeing, okay, from 2006 to 2050. So in the case of high demand scenario, so there could be about 4.4 gigaton of cement required throughout the world. All right. So that is the worst case or high demand scenario. So because of this, so the high demand for cement, meaning more emission of CO2 will be there into the atmosphere. So we need some sort of direction. So in terms of Portland cement supplement, or much better if we could find alternative to it. Much better if we could find alternative to Portland cement in order to reduce this environmental problem. All right, so here are some strategies that can be undertaken in order to curb or reduce emission caused by Portland cement production. So one of it is improving the current cement production technology by carbon capture and storage, right? So there are lots of strategies that fall under these categories, which are currently being practiced anyway in the cement industry. For example, the production of blended cement. If we talk about the EN 197-1 type of cement, so as we go down from cement 1 to the other 4 types of cement, so those 4 types of cement, except cement 1, are having some form of additive, which are mostly, not all, which are mostly byproduct-based material. So that is one of the technique that is currently being practiced by the cement industry in this particular regard. Other techniques could be to come up with a good absorbent that can try to capture the CO2 from being emitted, okay, in excessive amount to the atmosphere. All right. And the second one, minimizing Portland cement usage in concrete by replacing it extensively with supplementary cementitious materials. Okay, so this is the major focus of this presentation today. And the third one could be developing alternative non-Portland cement-based binders for producing economical and green concrete, such as that of alkali activated binder, also the geopolymers. All right, so I believe attempts towards reducing the consumption of Portland cement could somehow lead to reduction in potential environmental problem, including CO2 emission, reduction in cost, as well as preservation of the non-renewable natural resources, which as a whole could promote better sustainability of the construction industry. All right, so let us go back a little bit to basic, because what I'm talking today in terms of supplementary cementitious material falls under the what we call admixture, falls under the what we call as admixture. So in general term, supplementary cementitious material is also called mineral admixtures. Okay, so the materials here refer to finely divided material or any of those materials which are in powder form, which possess pozzolanic and sometimes and cementitious properties, meaning that some of this material are purely pozzolanic, while some are both pozzolanic and cementitious. So they can be used as part of concrete ingredient. Okay, so how do we use them? They can be used either to replace part of cement or as an additive to cement. Okay, so in either of these, they are normally incorporated to the batch shortly before or during mixing. So based on this, so this supplementary cementitious material very much fit the definition of admixture based on STMC 125 here. All right. And SCM here are mostly pozzolan or pozzolanic material. Okay. So what it is? So it is basically a siliceous, meaning SiO2 rich material, or siliceous and aluminous. So meaning that it is having either SiO2 rich or combination of SiO2 as well as Al2O3 rich material, which in themselves or in itself possesses little or no cementitious properties. So some may have cementitious properties, some may not have cementitious properties, right? But which will in finely divided form, so meaning that when these material are in powder form and in the presence of moisture, they can chemically react with calcium hydroxide and ordinary temperature to form compounds possessing cementing properties. Okay, so this is the fundamental definition of pozzolan. So based on this, so we see that the presence of moisture, so this is required, and then they can react with calcium hydroxide. So here we have to imagine the scenario in a Portland cement system, whereby Portland cement, once we mix with water, will undergo the process of hydration, which will form hydration products consisting of mainly calcium silicate hydrate as well as calcium hydroxide. So this calcium hydroxide here, okay, from the cement hydration, the availability of this calcium hydroxide will enable the pozzolan to react with it, okay, and to form calcium silicate hydrate, or some people call it secondary calcium silicate hydrate. So that is what is happening when we use pozzolan together with Portland cement. So meaning once the cement reacts, okay, and producing the hydration product, including calcium hydroxide, the cement will later on react with the calcium hydroxide to form secondary calcium silicate hydrate, which is the main binding material or agent in Portland cement, All right. So these are some examples of supplementary cementitious material, which mostly are byproduct in nature, except in the case of metakaolin and calcine shale. Okay. So from left to right, we can see fly ash class C, which is high calcium fly ash, on the most left, followed by metakaolin or calcine kaolin. So fly ash is byproduct from the electricity generating power plant that utilize coal as the fuel. Okay, and then metakaolin. Okay? So it is obtained by calcining kaolin at suitable temperature, normally in the range of 700 to 800 degrees Celsius for a certain period of time, to damage the crystal structure of the original kaolin to enable the kaolin to become reactive and transform into metakaolin, right? And then silica fume, and the next one, the third one, the black one. So it is a byproduct from silicon and ferrosilicon industry, right? And the next one is also fly ash class F. So it is having low calcium, all right? So this is the most widely used fly ash in Malaysia and throughout the world. Okay, and then followed by slag or ground granulated blast furnace slag. So it is a byproduct from steel production from blast furnace, and the last one calcine shale. So these are some, not all supplementary cementitious material. All right?
Yeah, jawab. Sebab tadi lah.
Okay.
Masa dekat
So
tadi
here
dengan, so aku lalu nampak dia ada,
you can see the
ada
comparison
apa, terbang punya terbangan.
in terms of chemical composition and some physical properties of ordinary Portland cement in comparison to some supplementary cementitious materials, specifically silica fume, metakaolin, MK, FA, ground granulated blast furnace slag, GGBS. All right. So from this, we know very much that OPC is very much calcareous, okay, consisting of CaO mostly, followed by SiO2, for example. So in the case of silica fume, it is very much siliceous, all right? And in the case of metakaolin, all right, so it belongs to siliceous and aluminous just now, right? Similar to fly ash, okay, siliceous and aluminous. Or in the case of slag, so it is having, all right, so it is having both properties of pozzolanic as well as cementitious because of the availability of SiO2 as well as Al2O3 and the content of CaO that is high here, all right? So based from this OPC, okay, oxide composition, so we can calculate the bulk compound composition, which is C3S, C2S, C3A, and C4AF here, all right? And down here, so it is given the data in terms of specific surface area, all right? So the bigger the surface area, meaning the finer the material. So it could be translated into the more reactive the material. So based on this, we could say that the silica fume, which is having 20,000 meters square per kilogram, as well as the metakaolin 15,000 meter square per kilogram, should be much more reactive than the fly ash, than the slag, based on the specific surface area. All right. So here's another material that has good potential as supplementary cementitious material. So we call it palm oil fuel ash. So what it is basically, it is the ash obtained, okay, after waste material, okay, from extraction process of palm oil that is happening in palm oil mill, which consists mainly of palm kernel shell, empty fruit bunches, and palm fibers. When they are used as fuel in palm oil mill to heat up boiler for generating electricity. So the resulting ash after the combustion of this waste material is called palm oil fuel ash, or just simply POFA. Okay, so some example, uncontrolled disposal of POFA may contribute to environmental problems. So meaning that if we don't use or don't dispose this material properly, so it may lead to environmental problem. Okay, so another view, close-up view of palm oil fuel ash, heap of palm oil fuel ash nearby a palm oil mill. All right, so at University of Science Malaysia, so some works have been undertaken to refine the material that we call palm oil fuel ash. So firstly, palm oil fuel ash, or WPOFA, waste POFA, from the palm oil mill, okay, is first subjected to drying, okay, and then subjected to screening, passing 300 micron sieve, right? And then the material is ground using laboratory scale ball mill, right? And then heat treated using gas furnace, and finally undergo a second stage ball milling. And the final material, sometimes we call it ultra-fine palm oil fuel ash, all right? So from the photo under here, so we can see the comparison between ultra-fine palm oil fuel ash on the left and ordinary Portland cement on the right. So this is some of the work that has been carried out at Science Malaysia. So this is the transformation that happened from POFA to GPOFA, ground POFA, to treated POFA, meaning that after subjecting to heat treatment, and finally after the second stage milling. All right, so this is the final product, the U-POFA. All right, so some analysis have been carried out to the material. All right, so in terms of chemical composition, as well as physical properties, particle size distribution, as well as specific gravity. All right, so when we compare these two types of POFA, G-POFA, meaning that after milling, and the U-POFA, which is after the final product, so we can see significant increase in the SiO2 and also an increase in Al2O3 as well as CaO. Okay, so that increase, okay, is in line with the reduction in C carbon content. or combustible carbon content, which reduced significantly from about 19% to less than 0.1%. Okay, so as a result of this reduction in carbon content and increase in the pozzolanic oxide, all right, so that turned the material into a very efficient pozzolanic material. Okay, so further analysis, comparing the G porphyr and U porphyr, showing a significant increase in the glassy phases from about 60% to more than 70%. So this is the amorphous content within the material, amorphous content within the material. And down here, so in terms of particle size analysis, all right, so we can see the difference between OPC porphyr, P porphyr, as well as U porphyr. All right, so there is a significant difference in terms of particle size, whereby the U porphyr is about 2.06 in median particle size, as shown down here. All right, in comparison to the T porphyr and G porphyr. All right, so meaning that the processes that have been undertaken to refine the material, so somehow we can claim it works to enhance the characteristic and the pozzolanic properties of the material. All right, so if you try to put this material in this ternary diagram, so it may sit here below silica fume, okay, because it is very much SiO2 rich material. Okay, so it should sit there above fly ash class C, class F as well. All right. Okay, so it should sit there as well. All right, and if we try to put it into this group of material, so it may fall somewhere here. Okay. All right, so this ultrafine palm oil fuel ash after the refinement process. Okay, so up there we can see the range for conventional concrete, for example, and then high strength concrete as well as nano engineered concrete. So meaning that in typical conventional concrete, we don't normally use material like silica fume, okay, or metakaolin. So we use that material, those material, for the case of high strength and high performance concrete. And in the case of nano engineered concrete, so sometimes we may require the use of nano silica, nano metakaolin, etc. All right. So we have used this material to produce high strength concrete. So the porphyr was used to produce high strength concrete at 20%, 40%, 60%, meaning we replace the ordinary Portland cement content at 20%, 40%, and 60%. Okay, while other materials remain the same. All right, and similarly, the other supplementary cementitious material, which is the silica fume, also down to the slag, ground granulated blast furnace slag, have also been used to produce high strength concrete, okay, at various replacement level, 3 for each, okay, 5, 10, 15 for silica fume, and metakaolin also the same, 5, 10, 15, fly ash 10, 20, 30, and slag 20, 40, 60%. So meaning that in this 60% slag concrete, so the ordinary Portland cement content is only 40%. It's only 40%. All right. So we look at the effect of this material in this particular slide, the effect of porphyr on fresh properties of concrete. This is high strength concrete. So meaning that we are using the palm oil fuel ash together with cement and other concrete ingredient, also together with a very efficient super plasticizing admixture or super plasticizer. All right. So, and the dose of SP was more or less constant for all mixes. So this is the observation. So meaning that in general, as we use the palm oil fuel ash or ultrafine palm oil fuel ash, so the workability based on slum tests tend to improve. The workability based on slum tests tend to improve. So this is a good thing. So this is a positive contribution of the material in the case of high strength concrete when used together with an efficient super plasticizer or high range water reducer. All right. And the figure at the bottom is showing the setting time test, and that was measured using proctor penetration resistant, okay, by preparing concrete mix and then sieving the mortar portion to be tested for penetration resistant. Okay, so based on this result, so we are seeing reduction or extension or increase in setting time as we put porphyr inside the concrete. And the more or the higher the replacement level of the porphyr, the greater the retardation in terms of both the initial and final setting of the concrete mixture. All right. So in the case of the other supplementary cementitious material, so this is the trend with regard to workability at constant water binder ratio as well as dose of superplasticizer. So we are seeing here that the material that is having significant water demand is the metakaolin. So the slump dropped significantly from about 100 mm in the case of the control or OPC concrete down to only about 5 millimeter for the case of the concrete containing 15% metakaolin. Sorry. All right. So this showing the significant increase in water demand for this particular material. All right. So in the case of other material, for example, silica fume, although it is a fine one, a very fine material, but since the superplasticizer is able to disperse the material effectively, and the material is having similar particle characteristic with that of fly ash, so it is giving higher slump at low dosage of silica fume of 5 and 10, slight reduction at 15%. So in this particular case, greater water demand could be more dominant. And we can see that fly ash and slag both are exhibiting reduction in water demand, especially in the case of the fly ash, which we can relate to the ball bearing effect from the particle characteristic of the material having spherical shape and smooth surface, etc. All right. So in general, in terms of setting, so the influence of the different SCM, supplementary cementitious material, in the case of the high strength concrete under investigation, so it tends to retard the setting of high strength concrete, both the initial set as well as the final set, and greater retardation in setting and higher content of this supplementary cementitious material, in particular in the case of the slag here, in the case of the slag. So we have to be careful in terms of our application, all right? And then we look at the effect on strength. So in this particular case, the palm oil fuel ash concrete, okay, the observation is basically enhanced long-term compressive strength in excess of 100 megapascal is very much achievable at up to 60% U-porphyr content, okay? So, and then the percentage ratio of U-porphyr contributes to the long-term strength development here, all right? So this, we can see that the material is, we can say it is efficient, okay? And it's able to improve the long-term strength, but not the early strength. If you can see the trend at early age of 1 up to 7, for example. So the concrete containing porphyr, in particular those with higher porphyr content exhibiting lower strength, but not at long term here, and not at long term. At 1 year, the concrete containing 40% U-porphyr shows the highest strength in comparison to the other mixes. All right. So in the case of silica fume and metakaolin here, so we can see in general, both material, okay, contributes towards higher strength of concrete in comparison to the control, okay, in particular for the case of the silica fume concrete. So based on this relative strength plot, we can see, all right, even at 1 day, so there is close to 10% increase in strength in comparison to the control concrete. And this could be associated to the filler effect as a result of the material that is being very fine, as well as probable or potential accelerating effect of OPC hydration because of the excessive surface area provided by silica fume, which enhance the reaction of cement or hydration of cement. All right. From then on, for example, we are seeing significant increase from there on. Okay. So we can see significant increase here. So that could be associated with the pozzolanic reaction of the material. Pozzolanic reaction of the material. Okay. So in the case of silica fume, at 5 and 10, so it is almost similar trend. So there is increase in relative strength, but at 15% there is a slight drop. So meaning that at 15%, so dilution effect may be more dominant at this particular stage at 15% metakaolin content because of the reduction in cement content. Nonetheless, if we compare in terms of the fly ash concrete, the long-term strength, no problem. Long-term strength very much achievable, greater than 100 megapascal in both fly ash as well as slag concrete. But when we want to see the early age strength, so we have to see from the relative strength plot. So there is significant reduction in early age strength, in particular those containing the 60% slag and the 30% fly ash, for example. But in terms of long term, so there is no problem. There is no problem, meaning that this material is able to develop strength greater than the control concrete, which could be linked to the pozzolanic reaction of the material with calcium hydroxide. All right. So in terms of porosity and water absorption, okay, here in the case of palm oil fuel ash concrete, so we can see the inclusion of this material leads to significant reduction in porosity and water absorption based on total porosity by vacuum saturation test. So here is a good point in terms of potential durability performance of the resulting concrete later on when we expose to aggressive environment, for example, because the concrete is having less porosity or lower porosity, less pores, and the penetration of aggressive agent from the potentially aggressive environment could be restricted better in comparison to 100% Portland cement concrete. All right, so in this particular case, it is showing coefficient of gas permeability as well as water permeability. So for both cases, we can see improved impermeability characteristic based on the two tests, gas and water permeability, which belong to transport properties of the concrete. All right, and tests related to chloride resistance were also undertaken. So in terms of the RCPT, rapid chloride permeability test, so we can see significant reduction in total charge pass, especially at the higher UPOFA content, right? And at longer curing period of 90 days, for example. Okay, so similar but slightly less effect in the case of chloride migration coefficient, but in general, okay, especially at longer curing period of 90 days, so the concrete containing UPOFA here exhibiting lower chloride migration coefficient in comparison to the control concrete. Okay. So some tests related to corrosion resistant characteristics was also undertaken. So based on impressed voltage test IVT. So here is the setup as well as the polarization resistance test and also resistivity measurement. So here are some of the outcome of the corrosion test. All right. So in general, significant reduction in initial current and average steady state current based on the impressed voltage test on the left, as well as steady state current on the right. Okay, especially at longer curing period of 90 days. All right. Here, corrosion current versus time based on the impressed voltage test. All right. So at 7 days on the left, A, B at 28 days, okay, up to D here 90 days. So meaning that the longer the curing period, so the better the resistance of the material or of the concrete containing UPOFA. So in terms of smaller corrosion current in comparison to the ordinary Portland cement control concrete. All right. So we can expect that if you use this material, it has the potential to provide better protection to protect the reinforcement within our concrete structure. Okay? And here it's giving time to reach initial crack under IVT test in hours. Okay, so for the 60% UPOFA, so based on the limitation of the test, so there was no crack observed. All right, but in the 40%, so crack observed at 7 days only, but at longer curing period, no crack were observed. In the case of OPC concrete, so in all sample subjected to 7, 28, 60, and 90 days, crack was observed. All right, and calculation of corrosion rate based on mass loss through the IPT in millimeter per year, there is a significant reduction in the corrosion rate based on this technique, okay, in comparison to the one in the control OPC concrete. All right. So here's what is happening within the microstructure of the material. So this test is to reflect the pore size distribution within the mortar, but the mortar was obtained by freshly sieving high strength concrete mixes. So meaning that after mixing, the concrete was sieved, passing 5 mm sieve to obtain the mortar, and that mortar portion were tested using mercury intrusion porosimeter, right? So what we can see, the black one in all cases is the OPC mortar, while the others mortar containing silica fume, metakaolin, etc. So in general, we can see there is a shift, a significant shift in the pore diameter if we compare the OPC with the other mortar, in particular for the silica fume, metakaolin, as well as the slag. In the case of the fly ash, the general effect is the same, but there is a slight, not that significant as in the case of the silica fume. All right. Someone raised hand here. Shall I stop or what?
Abraham Arif.
Yeah. Moderator, shall I stop and look at someone that raised hand, or we can discuss later? All right, I think I continue. All right, so this is a figure showing the pore size distribution in the different mortar mixture. Okay, so we can see significant trend, significant differences in terms of the trend. So based on this, the ordinary Portland cement or the control mortar is on the most left. So it is having significantly greater amount of macropores in the range of 30 to 50 nanometer, as well as greater than 50 nanometer. While those containing silica fume and the other mineral admixtures in general are having significant amount of smaller pores, okay, belong to this category, less than 15 nanometer, and there are some in the 30 to 50 nanometer. So that is what is happening. So meaning that most of the pores within the mortar or the concrete containing this supplementary cementitious material belong to the smaller pores or mesopores, while most of the pores within the ordinary Portland cement concrete belong to the macropores, which is greater than 50 nanometer, as well as some within 30 to 50 nanometer, within 30 to 50 nanometer. So this is the contribution of the pozzolanic reaction. So this is potentially also contribution of the filler effect of some of the very fine material like silica fume and metakaolin. And this also could be contribution of the effect on accelerating ordinary Portland cement hydration in the case of metakaolin as well as silica fume. All right. So this is how basically the material improve the microstructure of concrete. All right. Here's another set of results showing first in this particular column the porosity. All right. So in general, there is reduction in porosity. Okay. And so as well as there is reduction in both median as well as average pore diameter based on the mercury intrusion porosimetry test. Okay, so this showing the results. If we compare the control concrete or control mortar with those containing supplementary cementitious material. All right. Similar here. Okay, so this particular table showing the volume of pores in the different size range. Okay, so in the case of the OPC mortar, for example, small amount of or small percentage of pores in the less than 15 nanometer range. Okay, while for the mortar containing SCM, so they are having significant amount of pores which belongs to this category, especially the MK15, for example, 70% of the pores belong to the mesopores, which is smaller than 15 nanometer. Okay, so we can see similar trend in this particular range. All right. Here, for example, for the greater than 50 nanometer range, so we are seeing the control is having significant amount, while the others which contain SCM are having smaller amount in general. Okay. All right. So in the case of, we also use the palm oil fuel ash in the production of engineered cementitious composite. All right. So what we are seeing, the positive influence is that improvement in flexural deflection capacity and tensile strain capacity is the inclusion of the UPOFA. All right. M1, which one here is the control, while the others are having POFA, with POFA over cement at 0, 0.4 and 1.2. Okay. So reduce residual crack width after tensile test with UPOFA inclusion. Okay. The last one, C, okay, is the control without the POFA, while B is having POFA over cement of 0.4, okay, and A is having POFA over cement of 1.2 in terms of ratio. So we are seeing much finer crack, but with a bigger number of crack, or with greater amount of crack. Okay, in the case of ECC, containing the higher amount of POFA. All right, you can see the same scenarios. The case of A is the one with POFA over cement of 1.2, and in the case of B is the one without having POFA at the same water binder ratio. So A is having finer cracks and lots bigger amount of finer cracks, while B is having bigger crack with a smaller amount of cracks. All right, and then we see in terms of number of cracks, so increased number of flexural crack with the inclusion of UPOFA, increased number of flexural crack with the inclusion of UPOFA, and observation will also look at mid-span deflection. Okay, so higher mid-span deflection at maximum load with UPOFA inclusion. So that is the general observation. Okay, and in terms of drying shrinkage, reduce drying shrinkage with UPOFA inclusion at all water binder ratios. Yeah. And the potential of the material to undergo autogenous healing, okay, in pre-crack sample was also observed. All right. So in the case of the first one here, all right, so is OPC ECC, meaning without POFA. So we can see a significant crack of about 90 micron And the second one, B here, with porphyr over cement ratio of 0.4, so slightly smaller crack width. But in the case of the third one, porphyr over cement of 1.2, all right, so the crack is about 50 micron, but we are seeing that it's almost close. It's almost closing. So we can associate that with the delayed pozzolanic reaction, delayed pozzolanic reaction, the palm oil fuel ash with calcium hydroxide from cement hydration. All right. So attempts have also been performed to try to use the material porphyr here to produce alkali activated binder or alkali activated mortar as well as concrete. So the material porphyr was mixed with additive like ground granulated blast furnace slag as well as MK, all right, in small amount, as well as alkaline activators consisting of sodium silicate as well as calcium hydroxide, all right, and this porphyr based alkaline activated binder, we call it, all right. So research is still very much ongoing, okay, and there are quite a lot of interesting outcome from this research, which will be inshallah reported in the form of papers, etc. So here is a very just some result. So effect of curing time on composite strength development of porphyr based alkali activated mortar. All right. So in terms of different curing temperature, okay, at 65, 75, and 80 degrees Celsius. So we are seeing, so probably the 75 degrees Celsius is the more or less the optimum if you want to obtain maximum strength at 28 days. All right, so that's about some of the results from works that have been carried out in the concrete lab at University of Science Malaysia, School of Civil Engineering. All right, so here I list some which I claim as potential advantage of the material, the porphyr, as well as the other supplementary cementitious material. Okay, so possibly we can have lower material costs. So in the case of porphyr as well as fly ash and slag, since large volume of cement is replaced with SCM. So when we use especially this material at high volume, because the porphyr, for example, was used up to 60%. Similar in the case of slag, was able to be used up to 60%, while the fly ash maximum percentage was 30%. Okay. So recycling SCM to produce concrete avoids the need for landfilling or disposal of this industrial product, but in this case, not true for metakaolin. Okay, so if we don't dispose them properly, okay, meaning that if we don't use them in concrete, we need to find good ways of disposing them properly. Right. So by recycling in concrete, and at the end of the day, the concrete is having better, potentially better durability performance, that will be very good. Okay. And third one, use of SCM reduce or eliminate the need to mine virgin raw materials for Portland cement production and provide a constructive use for waste material. All right. And increasing use of SCM will significantly reduce energy use needed for cement and concrete production. Right. And increasing use of SCM can significantly reduce greenhouse gas footprint of concrete production by curbing CO2 emission from energy use and calcination in cement production. And we can expect better durability performance as the concrete produced or concrete containing SCM exhibit enhanced microstructure, engineering, and transport properties. All right. And in some of the concrete containing high volume of materials like fly ash, slag, and porphyr, so we should expect less susceptible to thermal associated cracking as bulk quantity of the cement in this concrete is replaced with this material. Okay. So, but maybe not true in the case of concrete containing silica fume and metakaolin, and people don't use them at huge amount as in the case of fly ash, as in the case of slag as well as palm oil fuel ash. Right, and then greener concrete through the utilization of less cement, translated into lower rate of extraction of non-renewable natural resources and lesser greenhouse gases emission, and extensive utilization of waste material, which if not utilized may lead to environmental problems. Okay, as well, we can expect lower whole life costs of concrete structures resulting from superior microstructure, engineering and transport properties of the concrete containing SCM, which could be translated into less maintenance and repair costs, especially when we expose our concrete structures to more aggressive environment. All right, so in terms of summary, the SCM proved to be highly efficient pozzolaning cement supplement, which could significantly enhance the microstructure, engineering and transport properties, as well as corrosion-resistant characteristics of the concrete. So more durable and greener concrete, in general high-strength concrete, because the example is on high-strength concrete, with lower cement content, lower material costs, and lower whole life costs could be produced via the extensive utilization of the SCM. And the POFA has shown promising potential as base material for alkali activated binder. In this case, as is totally eliminate the needs for the use of Portland cement. Last but not least, the whole efforts to extensively utilize SCM in Portland cement-based concrete, as well as alkali activated concrete, will definitely contribute towards better sustainability of the concrete industry. All right, so thank you very much.
Okay, thank you so much, Prof. Dr. Megat, for sharing a very good knowledge to us this evening. So, Prof. Megat, there is a question, one question for you. What are the challenges to the usage of this particular innovation on a larger scale? Will the material thrive well on a global scale?
Which one?
Which one? Abraham Arif.
Which specific material?
Can you please specific which material do you refer? Okay, maybe we can postpone the question to the end of the session because Abraham not yet. So I would like to invite our moderator, Professor Dr. Fadil.
Okay, thank you very much, Dr. Warid. Especially thank you very much to our first speaker, Dr. Prof. Megat. I think the question is referred to UPOFA materials. So I repeat the questions. What are the challenges to the use of these particular innovations on a large scale? Will the material thrive well on a global scale? It is referred to UPOFA materials.
All right.
Okay.
Okay. So, so I have to respond now or later?
I think you can respond now.
Okay. All right. So I think in terms of availability, so the material is, I would say, is available regionally in Malaysia, in Indonesia, maybe, I believe so, as well as in Thailand. All right. So if you're talking about global, so we may have to transform the material first, as in the case of UPOFA, then it could have potential to be used at global scale, as in the case of silica fume. For example, silica fume that we use locally, I believe it comes from overseas, either Norwegian countries or some from China maybe. Okay, so if the material is having significant potential and we are able to prove them, okay, and we are able to come up with the material ready, so in that case it can be potentially whatever, exported, etc., etc. So it depends. Okay, but in terms of availability, it is only regional in nature. Okay, the other challenge may be how do we get the significant quantity? Because if we just go to one mill, so the amount, if we talk about sustainability, may not be there. So we have to have, for example, a collection center or a few centers throughout the country or regionally in order to collect the material and set up one good processing plant somewhere that is able to transform the material to what we have done, as in the case of what we have done in the lab. So that is probably the strategy that could be done. If you want to ensure that the material could be regionally or locally available for the use of the concrete industry. Okay, is that okay?
All right, thank you, Prof. Magad, for the answer. There is another question from Yi Lun Lee. She's been asking about, she said, great work, Prof. Magad. Reason, can you give a reason for long-term strength reductions of metakaolin concrete? And the second question is there any metakaolin synthesized in USM lab?
Second one, what is the second question?
The second question, the second question is, what is the reason for long-term strength reductions of MK concrete?
The second one.
The second one, is there any synthesizing process of metakaolin in USM labs?
All right. So in terms of metakaolin, so what we have done basically in the lab is previously we purchased kaolin, processed kaolin from one kaolin industries in Perak somewhere. All right, and that kaolin was sufficiently fine, so meaning that we did not grind the kaolin. So what was done was only heat treated or calcined the kaolin at a certain temperature range, if I'm not mistaken, between 700 to 800 degrees Celsius. So that was the only process done. Okay. So the first question, which is mentioned about strength reduction or strength retrogression in the case of concrete containing metakaolin. So basically, it is not. There is no strength reduction. I believe what you are seeing is the relative strength plot. So because that is the strength of the material or concrete containing SCM relative to that containing ordinary Portland cement. Okay, so if you look at the actual strength curve, okay, so there is no reduction. Okay, so for example, there is no, more or less no reduction here. Okay, so this is the actual strength. All right, so meaning that up to 1 year, there is no reduction at all. Okay, so what we are seeing here is relative strength plot, meaning that we relate the strength of the concrete containing this SCM in comparison to the control concrete, in comparison to the control concrete. Okay, so it is not showing, or actually it is not showing reduction, but relative, because the OPC, the strength progress further at long term. So that's why in the relative plot, we are seeing like a reduction. But in terms of the actual strength, okay, so the metakaolin concrete did not drop in strength at all, but the OPC is still gaining strength. So that is the explanation that I could provide.
Thank you very much, Prof. Magad, for the answer. I think that will be the sessions of Prof. Magad. Now we proceed with our second speaker, Dr. Chaminda from the Sri Lanka. So without further ado, I would like to invite Dr. Chaminda to give his talk. Please, Dr. Chaminda.
Good afternoon. Can I share my screen?
Okay. It's clear. Thank you.
Right. Okay. So, good afternoon, everybody. So, it's like nearly 1 o'clock, 1 p.m. in Sri Lanka, and I think you know it's a global pandemic going on these days. I mean, we all are affected due to this COVID-19. So, I mean, the good part of that is, I mean, this kind of webinars. So, thank you for inviting me to join with this international webinar on construction materials and in Greenation era. So, in today's presentation, what I'm going to highlight is taking more local in context on the problems facing in Sri Lanka on the construction industry, which I'll be talking on alternatives for river sand. So I'm Chaminda, and this is kind of a study that currently going on with myself and Professor Nanakkara. So now, as the title explains, right, I'm going to talk on alternatives for river sand. So there are two keywords: river sand and alternatives. So the presentation that I'm going to do today, I'll be talking about river sand and why we need alternatives for river sand. That is the second part. And I'll talk about the alternatives. And specifically, I'll take one example and give you a little understanding about that alternative, which is more feasible alternative for river sand. So we all know river sand, right? That is the main source of fine aggregate, which especially, I mean, used in Sri Lanka. So if we take Sri Lanka, I hope you know that Sri Lanka is an island, and there are about 16 major rivers and about 30 minor rivers. You can see that starting by the central highland and ended by the Indian Ocean. So all these blue lines are rivers which cover the whole country. So river sand is one of the I mean, I'd say main source of fine aggregate in the construction industry. So sand mining is in all major rivers are happening in Sri Lanka. So there are few major rivers which I highlighted here. Due to the increase in the demand, heavily mined can observe in all these rivers at the moment. So if I take the cement consumption in Sri Lanka, so you can see over the last 20 years how the cement consumption increases. So I mean, we can based on the data that we got it, so by 2018 the cement consumption is 6.2 million tons that required for the national need. And also the interesting fact in Sri Lanka is 70% of the cement is going for house builders, which means small scale buildings that we are constructing using the 70% of the cement. So by considering the cement for consumption, and estimate by 2018, we can estimate like 20 million cubic meters of sand is required to cater the needs, construction needs. It's kind of a huge amount, right? And by considering the river sand, the supply, addressing or providing this much of sand for the demand is become impossible. So we have to find alternatives because of that. And I'll highlight key issues related to this high demand. So if you can see the graph here based on the price indexes, which is got it from Construction Industry Development Authority. So with the various studies, we can see that the orange line is the price index of cement, which you can see over the 20 years how it varies, and the river sand price index. So it's almost like in terms of Sri Lankan rupees, it's like 16,000 per cube, which is like $88 US dollars equivalent, which increased because of this high demand and for the last 20 years. So that increase in price mainly due to this shortage of river sand supply. So the demand is high, and that is one key issue in the construction industry. The construction materials, the cost or the fine aggregate cost gets high. Secondly, and mostly, the problem that we are talking about this, sustainable construction techniques, green and everything. So the main issue is with the environmental damage due to this uncontrolled sand mining. You can see two photographs of uncontrolled sand mines which happen in the country. So that's one of the key thing that we have to address as engineers and as people who involved in these kind of construction, responsible people in the construction industry. We have to find solutions. So though you can see a number of impacts due to this uncontrolled sand mining. So one of the main thing is coastal erosion. As we are an island, so that's one of the main, and the lowering of the riverbed rivers. Another major issue due to this uncontrolled river sand mining, and also salt water intrusion, riverbank collapse. That you can see in the photographs, like the bottommost photograph, left hand side. You can see the riverbank collapse, and you might think, what is this figure? A concrete structure. Right? This is recently building a salinity barrier over one of the rivers, Nilbala River. So it cost a lot. Why they are making this salinity barrier is due to the salt water intrusion. Now rivers are one of the key sources that we take the water consumption for drinking and other purposes. So seawater intrusion is a greater scale issue due to this uncontrolled river sand mining. So now now we know the problems, we know the issues. Now, what as an engineers, what is our solution for this one? We have to find some solutions. So if I list down some of the solutions, right? Now one could be restrict river sand mining at harmful locations, right? That is which means like sustainable extraction, right? of course we can do that, right? But that won't, cater for the demand, right? So now there are laws enforced in the country just to restrict river sand mining, and we hear the news on how illegally sand mining and things happen in the country. So the rules are there, but all the illegal things happen because we can't cater the demand by restricting the sand mining. So another point that we can take it to, overcome this uncontrolled river sand mining is reduce the demand for river sand by introducing practices like precast concrete building construction. We can go more into precast concrete building construction, and utilization of construction and demolition waste, improve workmanship, and also use of industrial byproducts. So I'll explain it when it comes to precast concrete buildings. So when we making precast concrete buildings, it's a well maintained construction process, which we can reduce the amount of the resources need to make precast structures, which will reduce the demand for river sand. And also we can use the construction and demolition waste as an alternative for river sand. And one of the key things which we can improve the workmanship. So as you can see this staircase, if we improve the workmanship of doing the construction, definitely we can reduce the amount of material that we are using for the finishers, right? So that the concrete is one example, and you can see the masonry work. So the effect of using non-standard size bricks, right? If it is standard size brick, so we can make the wall in a perfect manner, which is use less amount of resources or materials. But if it comes to non-standard size, then we have to apply extra mortar just to make that the structure start, aesthetically a good appearance, right? So in that case, if we can improve the workmanship by quality controlling or by close supervision, definitely we can reduce the demand for the river sand in terms of reducing the resources we are going to use for these constructions. And also nowadays, we can think of using the industrial byproducts. So one is bottom ash. It's a byproduct of coal combustion, which is used for power generation. So there is another way of reducing the demand for river sand. So that's something that we can think of, using these methods or these things to reduce the demand. And the third one, now we can alternative, or we can introduce alternative river sand and to overcome economical issues for the construction material. So now I think my presentation, I was explaining about river sand and the issues related to river sand. And now this part, now I was address about the issues and the alternatives to reduce demand for the river sand for construction. And in this part, I'm going to explain you about the alternatives for river sand. If we search about the alternatives, we can find different alternatives. I have already explained as two options: industrial byproducts and construction and demolition waste, which again come to a problem whether we can supply, we can fulfill the demand by using these two materials, industrial byproducts and construction demolition waste. Right? Then there are four more alternatives which we can think of. That is manufactured sand, which is M sand, or the quarry dust, crushed rock fine, which we refer as quarry dust mostly. So that is one. And the other one is also sand. And also in the literature we can find dune sand and alternatives for. Yeah. But when we consider the dune sand and pit sand availability, or the nature of how they create, then we should carefully use those resources as the fine aggregate need for the industry. I'll tell you an example. If you take it dune sand, right? Now this is a profile of a healthy beach, right? So you can see it's unlike the man-made materials. Dunes are taking like millions of years to make dunes, right? So that is a part of the coastal system, environmental system. So if we are going to extract sand from dunes, then again it will be a massive environmental issue, which we should really careful on proposing this kind of alternatives. Similarly for the pit sand. So especially when we come to dune sand, we should not encourage our engineers to use dune sand because of this the environmental issue. So out of the offshore sand and manufactured sand, I'm going to briefly give you an idea about the manufactured sand, because for the given time I thought getting one example of the alternative and give you a little understanding about the manufactured sand, which is not very common in Sri Lanka at the moment, which may be one of the best solution to overcome these environmental and economical issues related to the construction industry. So that is the second part of this presentation, which I was addressed about the alternatives. Now what we are talking is about the river sand and the issues related to river sand. Now I'll give you a brief about the manufactured sand or the quarry dust that we are using in the construction industry. That may be common for concrete nowadays, but in masonry it's very reluctant to use due to some of the properties in the M sand. Now, what is M sand? We all know that M sand is produced by crushing rocks, right? So when we say rock, we can't. Not all the rocks that we can use for M sand production, right? So I will brief about the type of rocks that we can use it for M sand later in this presentation. And usually quarry dust is a byproduct when we're making a coarse aggregate, right? So in some parts they are using quarry dust as it is as the fine aggregate, or we can produce M sand by making a process of washing and do all these activities to make it M sand. Somehow that is one of the alternative we can propose just to cater the demand for for the fine aggregate. Now, if we look at the closer look at the particles of the manufactured sand and river sand, you can see the manufactured sand, the particles are angularly in shape, right? We compare with the river sand, and rougher surface texture you can see, right? So those are, those are one of the, those are the key parameters which will negatively affect the properties of manufactured sand, which we can overcome by taking, relevant measures. So now, according to the standards, we say, particle sizes less than 75 micron or 0.075 millimeters. We'll define it as silt and dust. So the key challenge in the M sand is the higher amount of ultra fine particles. So that is one of the key challenge. But what happened when the silt and dust content or the particle size less than 75 micron is in a concrete or as a fine aggregate? So it increases the cohesiveness of water demand. Mainly the water demand is increasing, which resulted in the shrinkage, right? Which will ultimately reduce the strength of the either concrete or masonry that could happen at the end, right? So if that is the problem, we will be able to overcome this issue by using different methods. Basically, we can use chemical admixtures to overcome that. So which I'll again talk to you in a greater scale later part of this presentation. So these are the limitations according to the standards for the masonry work, blasting and rendering. For the masonry, ES1198, you can see the silt and dust content. For the natural sand, it should be less than 5%, but the crushed rock sand, which is like M sand, it should be less than 10%. Right? And also, when it comes to concrete, for the natural sand, it's less than 4%, and crushed rock sand, it should be less than 9 to 16%. Right? So now, as we know that the silt and dust content is high in manufactured sand, then we have to take measures to get the particle size distribution to the range which required to make a good concrete or mortar. Right? So which is a challenge, but we can overcome by introducing different techniques. Now, if we see the applications of manufactured sand, mainly it is used for road works, as you may experience this one maybe in your countries. And in the general use, we are using as a filling material and as a bedding material too. But when it comes to structures, using the M sand for the cement mortar or plaster is less popular. But for concrete nowadays, it's getting more and more famous in the higher mega scale projects, and also the cement blocks. So the issues related to M sand, if we address it, then we can definitely propose the M sand as a good fine aggregate for cement mortar and plaster, as well as small scale buildings for concrete and cement block itself. Now they are using. If we consider the availability of M sand, to the date, we are not making manufactured sand as a main product. Definitely, most of the cases it's like a byproduct. When we making the coarse aggregate, it's the byproduct, and also as I said, it depends on the rock type of the rock. So I think to overcome the issues related to the river sand, we have to make the manufactured sand as a main product, and byproduct itself is not sufficient to meet the increase in demand for sand. So if we take a geological map in the country, so there are quarries which we can identify in certain places, which may be able to make the fine aggregate to cater the demand in the construction industry. So when it comes to manufactured sand, so the main issues related to manufactured sand, as I said in one of the previous slides, right? Due to its the angularity shape and rougher surface texture, the workability of the concrete and mortar is reduced when we using the manufactured sand. So that's one of the challenge. Now, then we can think of chemical admixtures. When we using the chemical admixtures, again another problem arise, because some admixtures, when we using to make the concrete or mortar workable, it adversely affect the properties of the concrete or mortar due to the mineralogical composition of the M sand. So which is one of the key another parameter we have to address it. Anyhow, as engineers, we can overcome the first part of enhancing the workability. Secondly, the higher water demand, which can lead to high shrinkage, right? Again, we have to come up with the solutions which is not impossible task, we assume, as researchers or engineers. And as I said before, the mineralogical composition of M sand, which can affect the durability of the concrete and masonry mortar due to harmful minerals present in the parent rock. So the source of the rock that we are taking to make the manufactured sand is critical as we do the studies. Currently, we are doing another research studies on how this parent rock mineralogical composition affect the properties of concrete and masonry mortar. Because when we classify what are type of favorable or good parent rock types, which is giving positive impacts to the concrete and masonry, then it will be a good solution to overcome all these issues I said before. One last thing is the issue is behavior of chemical admixtures on M sand, which I said for enhancing the workability or reducing the water demand. So any case, we have to use kind of admixtures, but chemical admixtures behavior on M sand is something that we have to study, because that's one of the issues that faces in the industry. So I'll give you, this is the latter part of my presentation. So these are some studies that we are carrying out at the Department of Engineering Can you hear me? Can you all hear me? Yeah. Hello?
Yes, we can hear
Yeah,
you.
okay.
Yeah.
So, yeah, the current studies we are taking at the University of Sri Jayawardenepura, the first one is investigate the influence of parent rock material composition of M sand to the performance of concrete and masonry. So I'll give you a brief example of what exactly we are doing in there. So in Sri Lanka, we can find in common rock types, which is majorly available in throughout the country, right? So what we did was actually taking the rock samples from those different rock types and did mineralogical analysis to see the mineralogical composition. So we have published this paper. It is under review at the moment. So what we have found, out of these 10 rock types, only 4 types, which is charnocite, hornblende gneiss, intrusive charnocite, and granitic gneiss. Those are the 4 types which we found that is favorable minerals to produce aggregate. So other rock types, there are some unfavorable minerals like clay particles or particles like that is available, which may having adverse effect for the concrete or masonry mortar. So we are doing different type of experiments on this one. So you can see the figure XRD analysis for these 10 rock sample types, and we are doing XRF as well for the chemical composition of these types. So one of the finding, as I said, only these 4 types that we can use it, though the other types are available in the country. And also, as I said, we are in the study on investigate the behavior of chemical admixture on sand, right? That is also under studies at the moment. So the researchers are working on those projects. Once we address those major issues, I hope we'll be able to provide kind of design guidelines which will convince the industry on using M sand as an alternative for river sand, which something that we should do. Otherwise, the key 2 questions that I made it at the beginning, problems facing the country at the moment, which is the economical construction materials and environmental friendly or greener construction materials, we have to go for alternatives, which we are proposing here. So I think I'll summarize what I have explained to you throughout this presentation. I was talking about alternatives on for river sand. So the river sand and the problems associated with mining river sand is explained in the first part of this presentation, and then explained about the alternatives by understanding why we need alternatives, and then we explain about some alternatives, and out of the alternatives I just try to give you a brief about the manufactured sand, how we can use it for as an fine aggregate for construction industry. So there are issues in the manufactured sand which we can overcome by doing studies and giving solutions. So that's the end of my presentation. So I'd like to specially thank Professor Fadzil and the team from my UITM, and they have visited us almost 1 year ago, 12th of December 2019, right? Dr. Sheila and the team, Dr. Fatsil, they visited Sri Lanka. So lastly, I could say, you may all heard maybe about Sri Lanka. It's a very nice, beautiful country, and I have included few photographs of the country. So, I mean, due to these travel restrictions, we may not be able to travel as like before. But once the things are get to normalcy, it's a nice country to visit. So I'd like to invite all of you to, enjoy the, visit the country and enjoy the nature while having this kind of valuable conversations, discussions on technological improvement in this in the construction industry. So thank you again for inviting me for this session, and would like to get any questions. Thank you very much.
Thank you very much, Dr. Chaminda, for the very great presentations on MSAN. We do believe that this is the new trend in the construction industry. We are going to use the MSAN instead of using the natural sand for concrete industry. On behalf of the Concrete Society Malaysia, we are very uh, pleased on the presentations. Let us look if there is any questions. Okay, there is one question from Yi Lun Lee. Dr. Chaminda, I think it is any government incentive and legalizations to promote MSAN in Sri Lanka?
President Patil, at the moment, not really. This is the MSAN is something that used in the large-scale construction projects at the moment. As I said, we are not producing MSAN as a main product. So as I said, the small-scale buildings are using 70% of the cement, production or cement using in the country. MSAN is not going to that far. So there should be a kind of a way of promoting MSAN because anyway, this is again we are talking about a natural resource, but compared with the river sand, we have to minimize the environmental damage. So far we don't have that much of government incentives for MSAN, but I heard that there are things moving and things are developing because as I said, the bad effect or the adverse effect due to uncontrolled river sand mining is a major issue in the country at the moment. I think that addressed the question. Yeah.
All right, thank you, Dr. Jaminda. Just to share the experience, my experience. Actually, in Malaysia, we call it quarry dust, and instead of the quarry dust, they also nowadays they put it a name as MSAN. And for the time being, there is some bricks industry, okay, cement brick industry, using the MSAN as a replacement of natural sand in the productions of bricks. All right, thank you very much, Dr. Chaminda, for the information, for the knowledge shared with all the participants in this lively afternoon. Now we may proceed to the third speaker of the webinar series, which is Mr. Alex. Mr. Alex, are you here with us?
Yes, I'm here.
Yeah,
Thank you very much.
Mr. Alex. It's
Okay,
very nice
I want to
see
tell
you.
Doctor, I want to tell you first, I'm on my desktop and the
Right.
line is not stable here. So in case it breaks away, then you use my iPhone, the other one, okay?
Okay.
And both is online.
All right.
Both is online. Okay, let me start
That's good.
again.
That's good.
Ladies and gentlemen, my name is Alex. Okay, I'm not a doctor, not a professor, I'm not an engineer. Okay, but I'm in the construction line for over 40 years. To be exact, 47 years. I started at the age of 13. I was working for like 25 cents, US cents, 1 ringgit a day. So I've been working in the construction industry. I have to dig a big hole to make the footing and the pad and the stump and the ground beam, and then I become a carpenter, bar bender to make the columns, and I also become a bricklayer to lay the bricks and the plastering. So all this while I know that these are hard work and unnecessary. It took me 20 years to, when I grew up, and I invented certain crazy ideas in construction where it was 20 over years ago, no one believed it. But today, everybody seems to be using it, okay? So, doctor, shall we start with the slide?
Okay, Dr. Warid. Dr. Warid, would you please start the slide? Mr. Alex, you just tell us, is it the right slide or not? Okay, is this the one?
iPhone.
Mr. Alex, can you see the slide?
Okay, yeah, I think so. Yes, this is the one.
All right, so
Okay.
the presentation is yours.
Okay, let me just talk about it in a fast way. I think there is another one, right? Not this one.
Okay, I will share another slide.
I have been receiving a lot of what you call WhatsApp and message that a lot of Africans and Indian, Pakistan, they are
Is it the one, Mr. Alex? Mr. Alex, the line is not very clear. We already present you the slide. Is this the slide that you're looking for?
I'm not sure why. Not this one, another one.
Another one, Dr. Warid.
On the fourth one. Line is very, very bad.
Okay, why not? You're just using your handphone?
On phone on my slide.
On phone on my slide, you mean?
Can also.
Can also.
Can. That one is better. You may close your laptop and then you're using your phone.
Oh, can also. Wait,
Can also.
Okay. Have you seen the project?
No.
Slide?
This is not this one.
This is not this one. How come you? That's why you
one last one. Where
is that presentation?
Mr. Alex?
My one?
We only received that 3 presentation.
Okay, my one, can you see or not? Anybody can see or not?
No?
No, okay, put back the first one then. Put back the first one. Ask them to ask.
Okay.
Put back the first one.
All right, this one.
Okay, let's start with saying this. You see, the world,
okay.
I have been traveling for the last 20 over years. So I know about housing requirement. Also in Malaysia, also we require 1 million low-cost housing, affordable housing. The world requires, as of now, 400 million of houses. Every year, they require another 40 million units, you see. So why nobody is doing it is because the cost is very low. I mean, contractor and developer are not going to develop it because it's very low price. The price set is very low. So they rather go for better houses, you know, the profit is there. So the next slide, please. So my system that I developed is just a rough foundation. I call it a pad, strip, and a rough. So as you can see, now everybody around the world mostly also using a rough foundation. But there are ways for you to save on the rough, I mean the rough foundation. Because like I say when I was very young, we dig a big hole into the ground, and there's no need for all these weight, because the weight goes even like conventional way where the column and beam is. The way to carry the load is on from the beam, from the roof, all goes to the column.
Still like the line is very bad.
Hello. Excuse me, Alex. Hey, you have to switch off one of your device, you know. You have to switch off your device, one of the device. Otherwise, you switch off your computer. Just you rely on handphone. So
Because,
you have
yeah.
to switch off your computer in order not to have the echo.
Even the line also are very slow. I think it's better you use your handphone.
iPhone. Now I use my iPhone.
Yes, that's better.
Okay, but okay, y'all can see me, right?
Yeah.
Can you hear me?
Yes,
Everybody
we
can
can see
hear me,
you.
right? Okay. So as you can
Right.
see, now this is okay. Can you see the cursor? There's no cursor. Okay, look at the right picture and on the top. Okay, on the right hand side on the top, that is my what you call a pad strip footing. So where the wall is, we have a wider area, and where the all the load will go from this pad strip all surrounding the house, and where the hall is, where the kitchen is, and where the bedroom center, the center portion of the house, you don't need those thick rough foundation. A very thin, maybe a 2-inch, 3-inch concrete will do. Okay, and the wall is all casted at one go. The roof, it depends whether it is if you can see the picture on the below on the right left hand side, yeah. So this is a pitch roof. This pitch roof, it only consists of batten, and that's it. The roof is up, and if you can look at the right hand side, the bottom, that's the roof. It's like a hat. So if you have a flat ceiling, the wall is flat, so we prepare the ceiling, this the roofing, and we just put on top. That's it. I mean, this is like 1, 2, 3. This is a 2-day job to finish this house. Is there? And this house around the world, like in India, in Africa, in Pakistan, I've been doing it in now for over 50 countries. Is it? So I teach a lot of people to do house casting my way. Is it? So I know about a little bit about concrete. There's various kinds of concrete that we can use. Form concrete, or just pure cement slurry with foam, no sand. or with sand, or with plastic, waste, fly ash, sand. There's a lot. That to us there's 100 type of concrete to talk about. Okay, but I think the professors and the rest of the doctors know more about concrete than me. But to me, I have done all the actual hand mix myself, is it? Okay, next slide, please, doctor. Hello, doctor.
Yes, Mr. Alex.
Yeah, next slide.
Okay, yes, I already changed to the next slide.
Okay. So as you can see on the left hand side, the top one, these are the wall that we cast at one go. It can be a very small house, 300 square feet, 400 square feet. The center one, it can be a 2 rooms, 1 toilet. It could be 500 square feet. Or you see the larger one can be 3 rooms, 4 rooms. It can be 900 or 1,000 square feet. Everything is the same. It's only a matter of set up the formwork, reusable, put in all your door frame, window frame, electrical conduits, water pipe, and you cast in your concrete. See? So the next day you dismantle the formwork and set up, use the same formwork to set up the next house where the foundation is ready. Is it? So this is how fast we can do things, and this is 10 times faster than conventional method of doing houses. By the time you finish one column or a beam, I would have finished the house already. This is what is proven around the world now. Malaysia now only waking up to wanting to do this method now. For the last 15 years, very hard because a lot of red tapes involved. To get an approval, to get a project ongoing, it will take up to 2 years for all the departments, all the red tapes to get it going, is it? And all the CRIMs, all the CIDB, and all the JKR, all kinds of red tapes for us. That's why the world is accepting it, except Malaysia, where now slowly they are into it. As you can see, the one on the bottom left hand side, this house, it's already been done in Pakistan, in Karachi, and also in Uganda. They are going to do it in Kenya. And why I put this picture, because the actual house I actually has all the photo. I have hundreds of thousands of photos to show. But anybody can contact me, then I'll show them. I'll send by WhatsApp, anything. This is like one floor, but it has a half slab. I mean, the slab is a flat concrete where we can utilize the roof as a playground, garden, or a future second floor. Is it? The next slide, please. Okay. This is some of the equipment to make form concrete. Like one of the type of concrete, which is lightweight concrete. This has been my major business for the last 25 years, where I've been selling this forming agent and this forming generator and the mixer to my clients around the world. Okay. But lately in Malaysia, I'm not going to use form concrete. I may use a little bit, but I'm going to use self-compacting concrete, or I may go for geopolymer concrete. Because in Malaysia, we are going to start, instead of using reusable formwork, we are going to use stay-in-place formwork. Okay, the next slide, please. Okay, can you put up the video?
Yeah, sure.
Video 1 and video 2, and one is just a few seconds, so that people get the idea how it is been done.
Okay. Okay.
Okay, this is the second video, and never mind. You see, After 8 hours, the workers dismantle the formwork. This is setting up the formwork, and we pour in the concrete. Before we set up, we put a door frame, window frame, electrical conduit, sockets, and everything. This is one of the, to show you what is lightweight concrete. It floats in the water. We can make a floating house. We can make a floating house actually. Okay, the next slide, please. One more slide. Okay, this is one type of formwork which is very, very cheap. It can be reused 100, 200 times easily. It costs maybe like just a few dollars a square feet for the formwork, you know. A whole house may cost you like, you know, 40,000, 50,000 ringgit just to set up the formwork cost. You know, at the end of the day, it will cost you like only the few hundred ringgit for the formwork cost, you know, because the foundation may cost you like, if it's a small house, let's say for Malaysia, let's say we are talking of low cost housing, 800 square feet or 900 square feet. The foundation may cost you like 3,000 ringgit. The wall, plus the door, plus the windows frame and the door, the metal door frame and the openings, it may cost you like less than 15,000 just to finish it in 3 days' time, is it? So practically everybody can do it, you know. I would say that if you want to cast 10,000 houses, tutup mata lah, 1 year can finish it. Next house, next cast, please. Next slide. Video of a casted structure. What is this? I make so many presentations, I also forgot lah. We can use many types of concrete today. It depends on the engineers. If you depend on me to design, help you build and consult you, yes, I can consult. I know about. The first one, I know about concrete, is it? But if there are a lot of when the state, certain engineers, they want to prove this concrete because they've never gone study before, you know. They are not like us, you know, Dr. Padil. We have been studying lightweight concrete. But the first one, video one.
Video one.
Yeah.
Alex, we cannot see your face.
Oh, cannot see my face. But I have to open the other one when you can see my face.
Oh, I see. Okay.
Oh, can see my face already? Okay. My handsome face, huh?
Yeah. Everybody loves to see your face.
I'm 61 years old. No, okay, this is one of my formwork. This is a formwork, old one of the my patented formwork. It's only a 2-panel system. You just clamp on if it's one set. It's like a Lego. It's like a Lego. Next slide. This project is susah hati one lah, kena tipu ah. This developer, he built 500 units of this bungalow. It cost him 115,000 to build each conventionally. So I went in, I teach him how to do at the cost of 75,000 per unit. He saved 40,000 and he's supposed to give me 10% of his savings. He kicked me away after learning. Like karma lah, he died lah. Next slide, please. Okay, as you can see, these are the low-cost houses I'm talking about. You can see these are houses that cost maybe like $3,000 US dollar, maybe 12,000 ringgit, 9,000 ringgit, 6,000 ringgit. Yes, 6,000 ringgit, you can do a house, but very small. These are like houses in India, the rural parts of India, where all these houses are just 300 square feet. Is it? So you can see the flat roof, and it can be used as a second floor for future. Is it? As I can see the roof. You can make a roof just like a hat sit on top of it. Next slide, please. Like I say, my system is always 1, 2. 1 day for the foundation, 1 day for all the wall. If you are slow, 2, 3 days. Is it? But this is completely finished. I mean the foundation and the full structure of the wall. There's no column, there's no brickwork, there's no plastering. Is it? And then if you are not using this reusable formwork, you do not want to use formwork, you use stay in place formwork. Stay in place formwork is a kind of cement board like Hume, UAC, they are all approved, CRIM approved, Bomba approved, CIDB approved. So you use that as the formwork. I can teach you how to use it. Or you import or make this magnesium oxide board. They are like 6 mm to 8 mm thick. So it is stay in place. You pour in the chosen concrete. It depends what concrete you want to pour inside. From 5 MPa to 8 MPa, which is load bearing, until 12 MPa, 15 MPa, 20 MPa, even 100 MPa, so you can pour in. We can make concrete up to 200 MPa now. Next slide, please. Doctor, next slide. Okay, just casting wall. These are just casting wall, Like, okay, for instance, if you're casting a wall, you ask anybody in Asia, in Thailand, in Singapore, in Malaysia, anywhere, you buy bricks, you set up the brick, then you plaster, it will cost you 10 ringgit a square feet, which is equivalent to like $2.50 US dollar per square feet. But if you cast the wall with any concrete that I recommend to you, set up the formwork, pour in the concrete, skim coat it, it will cost you like 5 to 6 ringgit, which is like 50%, 45% cheaper than brick wall. And it's simple and fast and non-labor. You don't need a lot of labor like brickwork, cement renderer, and all these labors. So in another way, you can set up the stay in place formwork. You set it up, pour in the concrete, and the wall is ready for painting. Next slide, please. High rise, yes, the same thing. I mean, my specialist is in house, single floor house casting. But there are a lot of people will ask, hey, second 2 floor can, 4 floor can, high rise can. Yes, just for the wall. The savings is only on the wall, where it will cost you like 5 to 6 ringgit per square feet, or we are talking 50, 60 ringgit per meter square. If you want to convert to US dollar, just divide by 4.1 something right now. Whereas brickwork or panels or AAC blocks or other things will cost you like double the same price. Next, please. Next, please. So these are just sample house that I've casted before. These are just what we work on. Doctor, remember this, Dr. Hamida, and all the doctors in our concrete society. We have been working for the last 15 years, 18 years, I think. So we know about lightweight concrete. That's like the slide. Look at this alone. If I'm not mistaken, cement, there's 3 types in the world. We have 325, 425, and 525. If I'm not mistaken, 325 means cement alone with water, it has 30 over MPa compressive strength. If it's a 425, it has 42 MPa. If the 525, it has 52 MPa, megapascal MPa, compressive strength. That is pure cement. But if based on per meter cube, we are looking at 1,300, 1,400 kg per meter cube. So we put in sand and stone to make it into concrete. To add up the space, because these are cheaper things. So the strength reduced to 25 MPa, 30 MPa, you know. So like mortar is also considered concrete, cement and sand. But they are still heavy, 2002 density. Concrete is 2004 density. We are looking at, if we want to do a lightweight concrete, anything below 2000 is lightweight concrete. So we go for 1004, 1005, 1006 density, or even 1000, 1001, 1002. As you can see, this chart alone will tell you the compressive strength of 1004 density. And on the side, on the right hand side, you can see is the ratio of cement to sand. On the left hand side is the compressive strength, and in the days of 7 days, 28 days, and 60 days. And I tell you, I have kept some of the cubes for 2 years, 3 years, and it just keep on increasing the compressive strength. And nowadays, I've been working with fibers mixed into it, and it is just a wonderful new discovery. Next slide, please. Okay, I think that should be it. Time's up, right?
It's up to you, actually.
Up to me.
Is it the last slide?
No.
No,
okay, I can show some if they can want to see, there is some video here of I mean some you see, these are the stay in place. Can see or not? Boleh nampak? Huh? I cannot see you.
Can,
you cannot
but
see
not very clear.
Very clear. Hey, why Lazada come out already? Bloody fool. Nah, I don't. Okay, I have to go back to Zoom. Okay, you all can see or not? Can see this?
Cannot.
Cannot. How to see? Share screen. This time I'm a virgin boy in Zoom, so no choice. Okay, how to see? Okay, can see already. Okay, some video for you. You see this? This is formwork. It's a plastic formwork. So it's set up like 4 feet by 10 feet. So easy. And then pouring of concrete. Anybody wants to see how we pour lightweight concrete? This is how we pour lightweight concrete. And I think that's it. Okay. And so you're my lovely family. My grandson, my granddaughter, my son, my daughters. Okay, gentlemen, that's it for my presentation.
All right, thank you very much, Mr. Alex, for a very nice presentation. I do believe that this is the last presenter, but the first and second presenter have a link to the last presentations. Okay, because the first presenter, which is Prof. Dr. Megat, already present to us about the utilizations of supplementary cementitious materials, which is now becomes new trends in the construction industry. And then Dr. Chaminda are talking about M-SAN. And then finally, we have our speakers, Mr. Alex, who are utilizing the cements and the sand in order to produce a new kind of concrete. We call it foam concretes. and implement it into the constructions of walls without the structures, common structures that have been used before. So thank you to all the participants. Thank you to all the speakers for the great moments. I'm not sure, is there any questions? Let me check on the chat box first. All right. Okay. I can see there's a few questions here. The first question is, Mr. Alex, how about the durability of these structures?
Will last 200 years, no problem. Earthquake resistant. I don't think so. Up to 10 Richter scale lah. Maybe a few Richter scale, no problem. It's cyclone resistant, it's fireproof, and it's soundproof. It will last a couple of 100 years. Don't worry.
Second question is, how much MPA needed for 2-story house?
If it's 2-story, then we have to go for minimum load bearing at 25 MPa.
So the minimum strength is 25 MPa, is it?
Yes, if it's a single floor, I will just go for 12 MPa, 15 MPa. But in the standard, 8 MPa is considered load bearing. So we like any non-load bearing can be 2.8 MPa, 3 MPa, up to 5 MPa. That's non-load bearing walls. Load bearing walls are considered as 8 MPa above. So we use a minimum of 10, 12 MPa for our mix. But certain engineers, they may want to play safe, like you, doctor, when you are a student, you study from your professor. So when you come out, you teach, you add in a little bit play safe, additional play safe. That everybody additional. I have one engineer asking for 25 MPa for a wall. I mean, just all the wall of a single story house. What for, man? No need.
But based on your experience, you are successfully getting the foam concrete with a strength of 25 MPa, is it?
No, that is not foam concrete, only partial foam. It is considered self-leveling concrete. These are not low density, as low as 1500 or 1600. Those are at the range of 10, 12 MPa, which I would say is a safe for one floor house. It's load bearing, and moreover, we have reinforcement, which I use bamboo, no steel. Our starter bar, all our reinforcement is with bamboo strip, and our fibers is with palm oil fiber, coconut fiber, and bamboo fibers. But lately I use a lot of normal synthetic fibers.
All right. I think we still have a time. I think we still have time for a few more questions. Okay, the next question is from Mr. Yi. Alex, do you offer system rental such as formwork and PAM for or mass housing projects in Malaysia?
Of course, no problem. But you see, the thing is that if you want to build one house, I will just consult you how to build one house. You and your wife can build the house. Because you need to invest in mixer, pump, formwork. Okay? If you want to rent, it must be a minimum of certain amount of houses. Like 50 houses, 100 houses, 300 houses. If you're talking of one house, I will teach you how to do it. You know what is 3D printing? We are exactly like 3D printing, but it's just that we print one time to the roof. Whereas 3D printing is printing 1 inch with a big printer. Then the race after the one round, then they print and print and print and print and print and print up. Where we are building one house, I will teach you how to make a ground beam. It can be 6 inch. It can be 1 feet. The next day is another ground beam on top of the ground beam. Then the third day is ground beam on top of the ground beam. When you reach the window, you put your window. We reach the door, we put your door, and you put your pipings, your water pipes, your electrical conduit, your sockets, everything. And in a couple of days or couple of weeks, you will reach your roof, where it used to be the roof beam. At the end of the day, there's still no column. no beams, no brickwork. Is it? You understand what I mean? And it will be very cheap. You only need two planks. Two planks.
All right. Thank you for the answer. Maybe we can go on.
Anybody can see this?
Yes, of course.
This is what you call a stay-in-place formwork. It is so thin. It is just a board, okay? A very strong board. This board alone will last you 100 years. Okay? You paint it, set it up, pour in the concrete. The concrete can be just any concrete as long as it is load-bearing, strong, or non-load-bearing if it's just a wall, a putty wall. Set it up, pour in the concrete. All the waste, all the industrial waste in the world can be put into the cement and mix and pour into the house as the wall. Because this board is fireproof, soundproof already. It's ready for painting. You understand what I mean? It's so cheap to make a wall or a house. The rest, conventional method, if you're thinking of columns, brickwork, plastering, skim coat, beams, go and fly kite, ask them to. Honestly.
All right. Thank you for the answer. Let us see. Is there any other question? Okay, I think we have the last one, which is the question is, what is the design load per square meter? I think you have been answered the question before.
Up to them. We can, you see, in concrete, we can design any density to certain strength. Any certain range of density to certain strength. Certain, let's say like 1002 to 1004, we have this much of strength. 1005 to 1008, we have this much of strength. 1008 to 1009, we have this much of strength. And then on top of them, this is cement is the main bonding agent. We have sand and sand ratio, water ratio, silica fume, fibers, reinforcement. All this plays a part. But end of the day, a square feet of wall will be 50% cheaper than what you are doing conventionally. So before you want to build, any contractor wants to do walls, ask for my advice, because I never go to school.
All right. So thank you very much to Mr. Alex, and as an appreciation to all the speakers, we will provide presenter certificate, and to all the participants of the webinar series. You can enter into the link that has been provided by Dr. Warid Wazin, which is https://prompts.gle and the others. And please click on the link and then fill in the forms. Then you will get the certificate as well. On behalf of Society Malaysia, we would like to say thank you very much to all the participants of this webinar series. On behalf of Concrete Society Malaysia, University Technology Mara, University Technology Tun Hussein On, American Concrete Institute, and special thanks to Narotama University Surabaya for become a host of this program. Hopefully that we will meet again in futures. I pray that we will get good information, knowledge, and become more intelligent in improving the concrete industries for futures. Okay, once again, thanks, a special thanks to everyone. Now I pass back to the main host, which is University of Narotama.
Yeah, Professor.
Yeah. So is there any possibility that we can take a picture together? So everyone, please open up your camera. Can we open up all the cameras? So with that we can take a picture maybe.
Can okay. Boleh nggak?
Boleh.
There I can see that there is more than 70 participants in this evening. So can all the participants open up their cameras so we can take pictures together? Dr. Isan, is it okay?
Ayo. Camrul mana Camrul?
Dr. Warid can help as well.
Yeah, sure. I will take a shot when everyone open the camera. So I think we can take a shot for the picture for the memorable. Okay. So all right, give me a minute. Okay. So everyone ready? Okay. 1, 2, 3.
One more.
Okay, one more. Wait a minute. Okay, I will save this one first.
Make sure all the speakers is in the picture, Dr. Warid.
Yeah. Okay, we take another one. All right. So everyone ready? Okay, 1, 2, 3. Okay. All right. Thank you.
All right. Special thanks to all the speakers, Professor Dr. Megat, Azmi Megat Johari, Dr. Shaminda, and Mr. Alex. Thanks for a very nice and very good presentations. Hopefully that we will meet again in futures. And last word from me. Thank you very much and see you again. Bye.
Thank you.
Terima kasih, Profesor.
Thank you all.
Thank you.
Thank you, Mr. Dr. Isbani. Thank you,
Aziman.
Dr. Isbani.
Thank you to
Prof. Aziman.
Thank you, Dr. Aziman. Thank you, Nur Hazika. Mana Dr. Aziman? Tak nampak pun. Woi, makin handsome sekarang.
Eh,
More
Aziman. Aziman left the group. Why?
Left the group.
Left our group. Why? Wah, Aziman left.
Thank you, Faiz.
Which group? With you, Alex.
Huh?
Thank you, Pak.
Which group? Which group? I'm not sure. I must check. Maybe my phone has the problem.
No, you left our CSM group. Both the.
Thank you, Nur Fatihah. Thank you, Dr. Warid Wazin.
Okay, never mind, Mr. Alex. I will check.
Okay, thank you, Dr. Isbani.
Yes, go and let the university and me, the private sector, the developer, contractor, let's go and do a 10,000 unit of low-cost housing for Malaysia's homeless.
Sure, we can work on it. Now, Dr. Ahmad.
Mr.
No,
Alex, not me. Not me.
Yeah, I thought CSM should come up with a proposal to do that.
Yes, Dr. Lee.
Because you are not.
Ask you go and ask Muhyiddin or ask me for the land. So we do 10,000 houses per state.
Yeah, exactly.
But 10,000
you promote to the government.
Okay lah, 50,000 ringgit houses 50,000 Everybody happy what? They also happy.
Yeah.
We also happy. One house we make 5,000. Wow, 10,000 houses one house we profit 5,000 is 50 million only one state. So if times 13 state we can make 650 million. All of us share the multi-millionaire.
No. The thing is, don't worry about don't talk about the money first. You have to talk about
I'm a businessman. I don't talk money first.
Social enterprise, CSM social enterprise. It should be like this, So that
one more thing.
Yeah,
Dr. Lee, we get all these those students from all the university that are cannot become doctor, cannot become professor. They have to come out to the market. We train them to be house caster. So each of them can do a few hundred houses,
Yeah,
because
exactly. No,
it takes only a couple of days training to be a house caster. It's so simple.
Yeah, exactly. No, in my thought is like this, Alex. That's my thought, especially now, Dr. Aziman also around. You see, now you have to talk about how to create jobs,
Yes.
post-pandemic. So, in my opinion, whatever discipline, as long as your capacity building program is sustainable, because those people who fresh graduate from university, they are now not so easily employed,
You see,
So,
Doctor, you
this
see
is an opportunity.
this board,
Yeah.
they are so strong. You see this clip,
Yeah.
it costs only a few cents,
Yeah.
Just bond it here.
Yeah.
Bond it.
Yeah.
There's a clip.
Yeah. I understood.
Clip it in. The next one,
Yeah.
clip in.
Yeah.
So you have the formwork ready.
Yeah.
So you can pour in the concrete. The wall is finished for painting.
Yeah. But
this
of course,
board is soundproof, fireproof, CRIM approved, CIDB approved, JKR approved, everybody approved it. Is that?
Yep.
So it lasts, I think, easily 50, 60 years.
Yeah, indeed. So if we have got the volume, those whatever mentioned on the stay in place formwork has to be manufactured in China, perhaps, so that
those are MGO boards.
Yeah. Magnesium board, I know. I've been using that before.
Magnesium board
Yeah,
will
yeah.
only last a few years.
Yeah,
it
yeah.
cannot last external.
Yeah.
So what we do is we use the cement fiber board for external, and the magnesium oxide board for the internal.
Yeah.
And the concrete that we are going to pour in is going to be green concrete.
Yeah.
Is it?
The challenges is like this, let's assume that you have a medium size housing project, let's say 400 units, let's say 400 units, okay? So the first challenge is to come up with a site plan, because you see, based on normal site plan cost, let's assume that you have got a site plan with two mixer trucks. It will be around 1 million already, assuming that 300 ringgit per mixer truck. Of course, you can get you can get cheap one.
Because why? We don't need to mix ourselves or buy a single bag of cement. These are all supplied by the batching plant.
Of course, Alex is like this, You see, in a site that is not adjacent to the batching plant. That's why we always have to think about condition where it's not optimal.
Yes, simple, very simple also. I have been discussing a few projects. One in Triang, one in Terengganu, one in Nilai, one in Rantau, all few hundred units only. To me, my interest is in thousands one. Few hundred, I go and help out also. So I calculated each house. Foundation, we use self-compacting concrete, which costs only 200 over ringgit per meter cube, based on grade 30. Okay, easy. One day finish rough foundation. PRC A7 only. Okay, so the wall, whether it's in situ formwork, place in situ, I mean stay in place one, or reusable formwork. Reusable formwork.
Mr. Alex,
It's
we need
plastic,
station because we use this because this Zoom platform from Indonesia, so we need to stop the session now. I think.
Okay.
No problem. We discuss after this. We discuss after this.
No need to stop. Why? No. Anybody wants to go away now. We can still continue. Nothing wrong.
Because we use because this platform belongs to another university in Indonesia.
Oh, I see.
Sorry,
Okay,
Mr.
I open one more. I open another one, and you all join me. Who wants to talk?
we can arrange one special meeting.
Hey,
Yeah.
I just learned very easy. You go to Zoom there, make a new. I mean, just make a new one. Just put one. I give you the ID and then the password. You just join in only. That's all.
Yeah, and another thing that's my thought now anyway, because you have been venturing abroad, many countries, you mentioned Pakistan, India, and all the rest. In fact, each time you go to the countries, you should actively trying to link up with the educational institution and something like
India, China, Hong
yeah.
Kong, Thailand, Indonesia, yeah, even Pakistan. Link up already. I have all the university. I've been training them also at the university, just like UITM and you know, everybody knows about what I do. But like I say, my main thing is I want to get housing project. But all these people are majority, 99% or 90%, 95%. Once I train them, I teach them everything, they're going to do themselves. You know, I'm out of the picture.
No. You see what my thought is like this. You know, because now globally people are talking about carbon neutral.
I think we better put our own Zoom lah.
Chat group. Yeah, after
chat
this.
Group lah.
Yeah.
Doctor.
Yeah.
Kalau sana nak tutup, just tutup lah. After tutup already, we will open up WhatsApp
private
chat
one
lah,
Alex. Alex chat group lah for to especially under this CSM, you know, because it is being a non-profit organization, there will be opportunity as long as you have something viable, and then it is going to
Dr. Lee, from what I know, the world require 400 million.
Yeah, I know.
You take 1%, 1%, you are talking 4 million units, you know.
Yeah, I know.
You take 0.01% also, you cannot finish it.
Yeah, exactly. No, now I'm in my opinion, the most urgent one is to provide employment, you know, for those unemployed after university.
I think what I'm trying to promote is very good. But I'm
that's
so
why
disappointed.
now is a great opportunity for CSM.
Today, I'm very disappointed, you know.
Yep.
Because why? I was thinking a lot of people more people will come in, you know. 100 pun tak sampai I think I better become take the few hundred houses and make the 10-20 million sudah lah. Don't want to think a few hundred million lah.
Yeah, exactly. No. Now your mind should be focused on how to help the Malaysian who actually after graduate they cannot find job. You know, to me that's the most concern. To me, is most concern.
Yeah, we can easily train a few hundred housecaster, especially these CIDB, the class F contractor. These class F contractors, I can train them for a week. Then they can cast houses really.
Why not?
But the government is. I went and talked a few times. I went and talked a few times, you know.
Yeah.
Talk a few times to don't want to mention name now, okay? The top one now.
Yeah.
We are talking of 10,000 unit, 50,000 unit.
Yeah,
they are very happy. The price I tell them, they said 80,000. I said no need, 70,000, 65,000 also can.
Exactly.
Then they said medium cost. They said 1,000 square feet. I said, hey, I give you 4 rooms, 1,001, 1,002 square feet.
Yeah.
They say 180,000. I say, oh, no need, 150,000 below. Because each house, you give the land, I give back you the money later. I still can make 20, 30,000, you know, per unit. 10,000 houses, one house I make 30,000. I'm making 300 million, you know.
Yeah, I know.
Then I give them 200 million in the pocket money, you know. Then I take 100 million enough, I share with you enough, is that?
In fact,
but the problem is these bastards before even start work they already mint up that.
That's why you have to get to the right people and so on.
That's why
that's not easy.
That's why now I'm thinking a new strategy. Private developer, 1 unit, 5 unit, 100 unit, 50 unit. I also come. I help you.
Okay.
I help you.
Okay.
Because why?
Right.
We do the rough foundation. People doing 6,000 ringgit.
Yeah.
We can do 4,000 plus.
Exactly.
The whole house, column, beam, brick wall, plastering, any type of house, 1 floor, any design. We are looking at 3,000 square feet of wall, okay? 300 meters square of wall. They are doing is always at the range of 30,000 ringgit. The column, the structure, and the brickwork and the plastering, we are doing it 16,000 only. So I take it at 22,000, 20,000. Each house I can make 5,000 already. Then the rest, the roof, the painting, the door, the windows, the toilet, the tiles, the ceiling, the roof, everything the developer do back themselves. To us, it's just the foundation and the structure. That's it.